Bismillahirrahmanirrahim. Welcome to my YouTube channel Calculus and Mathematics Learning. This is the fourth video of exercise number 8.2, chapter number 8, Linear Algebra. So let's move toward exercise number 8.2, lecture number 11, BS Linear Algebra by Bernold, Kolman and David R. Hill, chapter number 8, Eigenvalue, Eigenvector and Diagonalization. This is actually the 8th edition. So in this video I will finish this exercise number 8.2 and I will start from question number 37. So from question number 37 to 40, show that the given matrix is not diagonalizable. So move toward question number 37. A is equal to 1 1 0 1. So move to solution. The given matrix is triangular matrix. Remember, when the entry is above the main diagonal, these are the main diagonals. So when the entry is above the main diagonal is 0, it means the given matrix is upper triangular. So when the matrix is either upper triangular or lower triangular, so their eigenvalue will be actually their main diagonal value. So in this case, the main diagonal values are 1 1. So the lambda and eigenvalues are 1 1. As the eigenvalues are repeated over here, so the theorem fails. Move to the next theorem. Ax is equal to lambda x. Shift x on the right hand side becomes lambda x minus x is equal to 0. Take x common, we left with lambda I2 minus a is equal to 0. Now by putting lambda 1 over here, it become I2 minus a into x is equal to 0. So I2 is actually 1 0 0 1 minus a is this matrix into x is xy is equal to 0. By subtracting these two matrices, it will give us this matrix. By multiplying this matrix with this, it will give us this. So from over here y is 0 and our x is not given, so let x is equal to arbitrary constant r is equal to 1. So my x1 eigenvector will be xy, so x is actually 1 and y is 0. So over here just one eigenvector is generated. My given matrix is 2 cross 2 order matrix. It means I need two linearly independent eigenvector, not one eigenvector. It means the given matrix is not diagonalizable according to this theorem. Now move to the next question, question number 38. Matrix is 2 0 0 3 2 0 0 0 pi. Move to the solution. The given matrix is lower triangular matrix because lower triangular matrices are those matrices in which the entries above the main diagonal is 0. When the entry is below the main diagonal is 0, it means the given matrix will be upper triangular. So in this case, the matrix is lower triangular because the entries above the main diagonal are 0. So when the matrix is triangular, so its eigenvalue will be the diagonal value, which is 2, 2 and pi. So from over here, eigenvalues are repeated, which is 2. So it means the theorem is failed. So use another theorem, lambda x minus x is equal to 0. Take x common. We left with lambda I3 minus a is equal to 0. Now first put lambda is equal to 2 in this lambda, so it becomes 2i3. So 2i3 will be 2 0 0 0 2 0 0 0 2 and minus a is the original matrix into xyz. Xyz is actually xo. Now from over here we get this matrix, and by multiplying these it will give us this. So minus 3x is 0, it gives us x is equal to 0. Minus 3z is equal to 0, it gives z is equal to 0. And my y is not given, it is equal to arbitrary constant r is equal to 1. So my x1 will be xyz. So x is 0, from y is 1 and z is 0. So this is the first eigenvector generated. Now by putting lambda pi in the same equation, so it becomes pi I3. So pi I3 gives us this matrix minus a is the original matrix into x is xyz is equal to 0. By subtracting these two matrices, it will give us this matrix. By multiplying this matrix with this, it will give us this matrix. So from over here 3x is equal to 0, so we get x is equal to 0 implies minus 3x plus 3y is equal to 0, so put x 0, it will give us y is equal to 0 implies my z is not given, it is equal to r is equal to 1, so x2 is xyz. Now my x is 0, my y is equal to 0 and z is equal to 1. From over here another eigenvector is generated, but remember my given matrix is 3 cross 3 order matrix. It means I need 3 linearly independent eigenvector, not 2 eigenvector. It means the given matrix is not diagonalizable according to this theorem. Now move to the next question, question number 39. Matrix is 10 11 3 minus 3 minus 4 minus 3 minus 8 minus 8 minus 1. Move to solution. First we are going to find the value of lambda by using formula f of lambda is equal to determinant into lambda I3 minus a. So lambda I3 is this matrix minus a is original matrix. Now by simplification, it will give us lambda minus 10 minus 11 minus 3 3 lambda plus 4 3 8 8 lambda plus 1. Now finding the determinant by expanding with r1. So per lambda minus 10, I cross first row and first column. I left with lambda plus 4 into lambda plus 1 and minus 8 into 3 minus 24. Now for this it becomes plus 11 because plus minus plus. So minus into minus plus 11 for this cross this row and this column. So 3 into lambda plus 1 and minus 3 into 8 minus 24. Now for minus 3 comes down, it is cross this column and this row. So 3 into 8 24 and lambda plus 4 into 8. So by simplification, it will give us f of lambda is equal to lambda cube minus 5 lambda square minus 13 lambda minus 7. Now over here, by parallel simplification, it becomes lambda plus 1, lambda square minus 6, lambda minus 7. From over here, lambda plus 1, I get lambda is equal to negative 1. And from over here, lambda square minus 6, lambda minus 7. By factorizing, I get lambda is equal to minus 1, lambda is equal to 7. So over here, three values of lambda eigenvalue are generated, minus 1, and 7. So minus 1, this is repeated, eigenvalues are repeated. So the theorem will proceed to the next theorem, x into lambda I3 minus a. So put lambda, the repeated value, minus 1 over here. So minus I3 minus a. Minus into I3 is this, minus a is original matrix. By simplification, over here I get minus 11x minus 11y and minus 3z is equal to 0. 3x plus 3y plus 3z is equal to 0, and 8x plus 8y is equal to 0. So it becomes x is equal to negative y. From over here, by putting x negative y, it becomes 3z is equal to 0. So z is equal to 0. Now I consider y is equal to r is equal to 1. So my eigenvector will be x1 is equal to xyz. So my x is negative y and y is actually r and z is equal to 0. So y is r, so minus r 0, so r is 1, so minus 1 1 0. So by putting minus 1 in lambda, in place of lambda, we get one eigenvector, and by putting 7 we will get another eigenvector. So two linearly independent eigenvector is generated, not three linearly independent, because the given matrix is 3 cross 3 order matrix. So we need three linearly independent eigenvector, not two linearly independent eigenvector. It means this given matrix is also non-diagonalizable according to this theorem. Now move toward the question number 40. 2 3 3 5 3 2 2 3 0 0 1 1 0 0 0 1. So 4 cross 4 order matrix is given. Using definition, f of lambda is equal to determinant lambda I4 minus a. So lambda I4 is this identity matrix, minus a is the original matrix. By simplification, it gives us this matrix. Now I finding the determinant by expanding with R4. So over here, this and this and this will give us 0. So I left with lambda minus 1. So for lambda minus 1, cross this row and this column. So I left with lambda minus 2 minus 3 minus 3 minus 3 lambda minus 2 minus 2 0 0 lambda minus 1. Now again expand with R3. So for lambda minus 1, I will cross this row and this column, and lambda minus 1 will comes outside just like this lambda minus 1. So lambda minus 1, this lambda minus 1. So I left lambda minus 2 into lambda minus 2 whole square, and it becomes minus 9. Now from over here, I will get 4 values of lambda 1 1 minus 1 pi. So eigenvalues are repeated. Proceed to the next theorem, because this theorem is paid because eigenvalues are repeated. So lambda I4 minus a into xo. So by putting over here, the eigenvalues which is repeated is actually 1. So I will put 1 over here, not these distant values. So by putting 1 over here and by doing simplification, I will get just one eigenvector. How? Lambda is 1, so I4 minus a. So from over here I get this matrix. So I will make a linear equation, minus over here minus 3x minus y minus 2z and minus 3t is equal to 0. So from over here t is 0. So by putting t0, I get this. Now after this, so minus x minus 3y minus 3z minus 5t is equal to 0. By putting t0, I will get this, multiplying with 3, so it becomes this. Now subtract this and this, it will give us this equation. So y is equal to minus 7z by 8. Let z is r. So by putting zr, it becomes y is equal to minus 7r by 8. By putting y in this equation, so it will give us x in term of r, which is minus 3r by 8. Let I assume r is equal to 8. So from over here I will get x, y and my z and my t is 0. So it will give me just one eigenvector. By putting minus 1, it will give us another eigenvector. By putting 5, it will give us another eigenvector. So 3 linearly independent eigenvector is generated, not 4. Because the given matrix 4 cross 4 order matrix, I need 4 linearly independent eigenvector, not 3. It means the given matrix is not diagonalizable according to this theorem. Now that tells that a matrix A is called defective if A has an eigenvalue lambda of multiplicity m greater than 1, for which associated eigenspace has a basis of fewer than m vector, that is the dimension of eigenspace associated with lambda is less than m. From question number 41 to 44, use eigenvalue of the given matrix to determine if the matrix is defective. So question number 41 is a matrix is 8 7 0 8 while lambda values is given 8 8. So move to solution. First of all, the given matrix is triangular because these are the main diagonal values, so the entries below these main diagonal is 0. It means the given matrix is upper triangular matrix. So when the matrix is upper triangular, so their eigenvalue will be their main diagonal, which is 8 8. So we need to find the eigenspace associated with lambda is equal to 8 of multiplicity m is equal to 2. Over here this eigenvalue 8 is repeated twice. That's why I write m is equal to multiplicity 2. So lambda x minus x is equal to 0. Take x common, we left with lambda I2 minus a into x is equal to 0. By putting lambda and inserting lambda and plug in lambda 8 over here, become 8i2 minus a into x is equal to 0. So 8 into i2 gives us this, minus a is the original matrix, into x is xy is equal to 0. By subtracting these two matrices, it will give us this matrix. By multiplying this with this, it will give us this matrix. So minus 7y is equal to 0, it means y is 0. My x is not defined, so let x is equal to r is equal to 1. So x is xy, so x will be x is r and y is 0. So r is 1, so 1 and 0 will come down as it is. Now basis for the eigenspace associated with lambda is equal to 8 is just one eigenvector, which is 1 and 0. So the dimension of this eigenspace is just 1, which is fewer than m is equal to 2. It means our matrix A is defective. Now move to the next question, question number 42. 3, 0, 0, minus 2, 3, minus 2, 2, 0, pi, lambda values are 3, 3, pi. We need to find the eigenspace associated with lambda is equal to 3, because 3 is repeated over here. Of multiplicity m is equal to 2. 2 twice it is repeated twice, so m is equal to 2. So using equation x into lambda I3 minus a is equal to 0. So x will come down as it is. Lambda is 3 because 3 is repeated. So 3i3 and minus a into x is equal to 0. So 3 into i3 gives us this matrix. Minus a is the original matrix. By subtracting these two matrices, it will give us this matrix. Now from over here, it becomes 2x plus 2z is equal to 0. So x will be equal to minus z. Now my x and z is not defined and y is also not defined. So let y is t and z is r. So by putting z r over here, it become x is equal to negative r. So x is xyz, my x is minus r, my y is t, and my z is r. So over here two condition is generated. For r is equal to 0, t is equal to 1, it will give us 0, 1, 0. And for r is equal to 1, t is equal to 0, over here it will give us minus 1, 0, 1. So the dimension of eigenspace is 2, which is x1 and x2, which is not fewer than m is equal to 2. It is not pure because these are equal to and 2 are equal, not pure, which is not pure than m is equal to 2. It means that a given matrix A is not defective. Now move towards the question number 43. 3, 3, 3, 3, 3, 3, minus 3, minus 3, minus 3 is a matrix with lambda is equal to 0, 0, 3. So move to solution. We need to find the eigenspace associated with lambda is equal to 0 because 0 is repeated twice. Of multiplicity m is equal to 2, it repeated twice, so I write m is equal to 2. So x into lambda I3 minus a is equal to 0. So I will find the solution to the eigenvector for lambda is equal to 0 because this is repeated. So by putting lambda 0, it gives 0. So I left with minus a into x is equal to 0. So multiply the given matrix by negative, so it become minus, 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 it become plus, plus, plus from over here. And x is xyz is equal to 0. Now become replace, interchange this third row and first row over here. And after this row, divide the first row with 1. This is actually the reduced row echelon form. This is some operation used. And add this row with this, it becomes 0 whole. And this row will come down and divide the first row with 1. So from over here, x plus y plus z is equal to 0. So not y is defined, not z is defined, not x is defined. So I consider z is equal to r, y is equal to t. So by putting y, t and z are over here, so I will get x is equal to minus t minus r. So my x is xyz, so x is minus r minus t, and my y is t, so put t over here, and my z is r, so put r over here. Now I have two conditions, r is equal to 0, t is equal to 1, it gives us this from over here, and by putting r1 t0 over here, it will give us x2. So basis for the eigenspace associated with lambda is equal to 0 is 2, because I get x1 and x2. So it means that basis is 2, which is not pure than m is equal to 2. So it means the given matrix is not defective. Now move to the next question, question number 44. 0, 0, 1, 0, 0, 0, 0, minus 1, 1, 0, 0, 0, 0, minus 1, 0, 0, with lambda is equal to 1, 1, minus 1, minus 1. Over here we have two cases because 1 is repeated twice and minus 1 is repeated twice. Move to solution. We need to find the eigenspace associated with lambda is equal to 1 for m is equal to 2 because 1 is repeated twice. So x into lambda I power minus a is equal to 0. So x will be x, y, z, t. Let's suppose lambda passport 1. So 1 into I power minus a. So 1 into I power is this minus a is original matrix into x is x, y, z, t. From over here by subtracting it gives us this matrix. So from over here this is x, this is z. So x minus z is equal to 0. So x is equal to z. And from over here this is y and this is t. So y plus t is equal to 0. So y From over here, this is t. So t is equal to 0. T is equal to 0. So by putting t0, we get y is equal to 0. Let x is equal to z is equal to r is equal to 1. So x, y, z, t. X is equal to r, y is equal to 0, z is equal to r, and t is equal to 0. So over here we get just one eigenvector. So this one eigenvector is actually the eigenspace, which is actually 1 less than 2. So in this case, the given matrix is defective. Now in this case, minus 1. So by putting minus 1 in the same formula, so it becomes minus I power minus a is equal to 0, and I power is this, a is this. By subtracting, it gives us this matrix. So it becomes minus x minus z is equal to 0, so x is minus z. From over here, minus y plus t is equal to 0, so y is equal to t. So let z is equal to r, so my x will be minus r. And by putting, let's suppose t is equal to u, so by putting t u, we get y is equal to t is equal to u. So x, y, z, t. So x is minus r, y is u, z is r, and t u. Per r is equal to 0 and u is equal to 1, we get this matrix, and per r is equal to 1, u is equal to 0, we get this matrix. So in this case, per minus 1, we get 2 eigenvector, which is equal to the eigens, which is equal to m is equal to 2. So in this case, the given matrix is not defective, while in this case, the matrix is defective. Now move toward the question number 45. Let d is equal to 2, 0, 0, minus 2. Compute d power 9. Move to solution. My d is 2, 0, 0, minus 2. We are going to compute and find d power 9. So just take power 9 in this whole matrix to it become 2 power 9, 0 power 9, 0 power 9, and minus 2 power 9. 2 power 9 is equal to pi 1, 2, 0 power 9, 0, 0 power 9, 0. And minus 2 power 9 is minus pi 1, 2, because when the power is odd, so the sign will comes down as it is. So minus will be minus. If the power is even, so over here we will then write plus. But over here the power is odd, which is 9. So we will write minus. So 2 power 9 is pi 1, 2. So the required d power 9 matrix is equal to pi 1, 2, 0, 0 minus pi 1, 2. Now let's understand the last question of exercise number 8.2. Last question is 46 number question, and this question is very important, and this is the last exercise number 8.2 with which this chapter will be completed. So it tells that let a is equal to 3 minus pi 1 minus 3. Compute a power 9. So first of all, I will find the diagonal matrix. Lambda 1, lambda 2 is actually their eigenvalue. Remember, in the diagonal matrix, the eigenvalue is actually the main diagonal value and the non-diagonal value will be 0. How to find lambda 1 and lambda 2? First, we will use the formula that d is equal to p inverse into ap. So shift this p inverse on this side, it become dp. So dp is equal to ap. Then shift this p on this side. So over here the power of p is 1. So by shifting to the left hand side, it become p inverse. So p inverse dp and so on. Now we are going to find the value of a power 9. So from over here we can cancel this p inverse and p, so it become a is equal to d. So it become a power 9 is equal to d power 9. That's why we cannot take the power 9 on these both of them. So it become a power 9 p d p inverse whole power 9. So it become p d power 9 p inverse. So remember this step. Now if of lambda is equal to determinant lambda I2 minus a. So lambda into I2 is this identity matrix, minus a is the original matrix. So from over here we get this. Now by taking the determinant and by simplification, we get lambda square is equal to 4. So we get two values of lambda 2 and minus 2. So the lambda 1 will be 2 and lambda 2 will be negative 2. So my diagonal matrix will be 2 minus 2 and the non-diagonal entries are 0. So over here we use x into lambda I2 minus a for finding the eigenvector. So first put lambda 2 over here. So by putting 2 and by doing simplification, it will give us plus eigenvector. So per r is equal to 1 plus eigenvector x1 is pi 1. Now by putting lambda 2 is equal to minus 2 in the same equation, it will give us another eigenvector x2 1 1. So my p is actually x1 x2. x1 is the plus eigenvector pi 1 and x2 is the second eigenvector 1 1. Now finding the determinant of this matrix and then finding the adjoint, and then we will easily find the inverse of this matrix using the formula a power 9 is equal to p d power 9 p inverse. P is given this matrix, d is we already find out from the eigenvalue this. So taking the power 9, so 2 power 9 is pi 1 2 and minus 2 power 9 is minus pi 1 2, and these non-diagonal entries will be 0. Into p inverse is this matrix we find out from p by using 1 over determinant of p into adjoint of p per 2 cross 2 order matrix. So it will give us this matrix. Now by multiplying these three matrices, it will give us a power 9 7 6 8 minus 1 2 8 0 2 pi 6 minus 7 6 8.